Good morning. Welcome to a strangely brighter than before room. It's weird, but I'll take it. We're going to talk about binary search trees today. New topic, separate from hash tables. And I really like these. It's a neat data structure. The introduction to the concept, like talking about binary search trees themselves, won't be too bad. We're going to actually do a diversion into graphs first, and hopefully that'll still be a review. And then once we start talking about the data structure itself, it still won't be too bad. But binary search trees have sort of this one fatal flaw that prevents them from being as useful as they may initially seem. And there are ways to get around said fatal flaw, but they make the data structure much more complicated. So although this is going to be relatively easy compared to earlier stuff, I want you to still take binary search trees seriously, because we're going to see many more trees that get much worse. So the motivation for binary search trees is once again just trying to make certain operations faster, trying to preserve the advantages of certain data structures without having their disadvantages, and then just dealing with whatever new disadvantages come along the way. We learned about hash tables that give us constant time complexity for insert, search, and delete, but make it basically impossible to do an in-order traversal. On the assignment, I said that the method to print all the fish that you have in your inventory doesn't need to print the fish in sorted order. That's why. In a hash table, your elements will be ordered by whatever the hash function gives those items for array indices. Whatever array indices the hash function gives the items. And that will be probably completely different from whatever ordering you would put them in, and also have several gaps. So if you want to print out the contents of a hash table in a specific order, you might want to copy all of its contents into another array, sort that array, and then print it. That would be n log n, because the copy would take big O of n time, one copy operation for each element. And then the sorting, that would be something that you learn about in Comp 2080, or maybe a first-year course. But the time complexity of the best sorting algorithms that are feasible to talk about at a first or second year level are n log n. So if you want fast insert, search, and delete on a sorted data structure and fast reversals, you'll have to look into alternatives. And also another motivation is that linked lists are good with being flexible about memory usage. So you don't have to allocate a big chunk of memory once and then be limited by that size like you would be with arrays. But then inserting in order and especially searching for an element gets really tedious. It's always linear time because you have to go through the nodes one by one. So binary search trees will solve both problems and then get weird. We'll look at that soon. But first, we have to dip our toes into a bit of graph theory. Anyone who's taken Math 1240 should be familiar with this, but I know not all of you have. I'll go through it somewhat quickly, but still pretend that you've never seen this before. A graph is a set of things and the connections between them. We call the things nodes or vertices, and the connections between them edges. They're super useful for modeling a whole bunch of things. If you're making some sort of transportation software, the nodes could be buildings or cities, and the edges could be the roads between them. If you're modeling a network, the nodes could be computers, and the edges can be the connections between them. You could do some pretty interesting sociology where the nodes are people and the edges are the relationships between them. Basically, any situation where objects might be paired with each other is useful for graph theory to talk about. These are all examples of graphs shown graphically, fittingly enough. From this representation, it probably isn't obvious how you might store them on a computer in a program, but we'll get to that too. This is just one node by itself. This is 3 nodes by themselves. And this is what's called a complete graph. All of the nodes are connected, or every pair of nodes is connected by an edge. The edges in a graph can be directed. Maybe if you're modeling buildings and streets, a directed edge can be like a one-way street. So one node is identified as the start of the edge, and the other is identified as the end, like beginning and destination. And to draw them, we put a little arrow on the edge to show that, in this edge's case, this is the start and this is the end. And now we're getting closer to our data structure. A tree is a directed graph with no cycles. This special case of graphs is useful for showing any sort of hierarchical relationship among data. We could, in this case, say that nodes B, C, and D are below or contained by node A. We assume that all of the edges are directed and flow downward, but since that convention, that assumption is so consistent, we don't bother drawing those edges. Don't bother drawing the arrows on the edges. Oh, and to give another example that might illustrate the hierarchy idea, a nice application of this is folders and files on your computer. A being above B, C, and D could mean that A is a folder that contains folder B, folder C, and D, which is either a file or an empty folder because it has nothing below it. We call the topmost node of a tree the root. There's a joke that goes around that computer scientists call these trees even though they're clearly upside down from what you would expect a tree to be in real life because they've never gone outside and they've never seen a real tree. So according to that, that's why the root is at the top of the tree. When one node is above another, we say that it's the parent of the lower node. So in this case, A is the parent of C, and C is a child of A. Coincidentally, another very good application for trees is modeling a family tree with the parents and children representing parents and children. Wait, no, that's not how it would work at all. Forget I ever said that. Anyway, generalizing the notion of parents and children, we say that A is an ancestor of K because K is the child of a child of a child of A, and likewise K is a descendant of A. In more graph theoretical terms, we say that there's a path from A to K, but don't worry about that. There's a sequence of edges between them. continuing to abandon the plant metaphor for a family metaphor, we say that nodes on the same level of the tree are siblings. In this case, B, C, and D are siblings. If you draw a graph or a tree like this, all siblings will be at the same vertical position, the same row. And then more abstractly, like if you're modeling this as like an array or a bunch of objects with references between them, you'll know that nodes are siblings if they have the same parent node. Finally, back to plant terms. The leaves are the nodes that have no children. Any node that is not a leaf is an interior node. The thing in the blue box here, we call a subtree. You might also hear it referred to as a branch. And it's a single node and all of its descendants. You'll notice that a subtree is itself a tree, which gives us a kind of neat recursive definition for a tree. A tree is either a single node, so like in this case, just H is technically a tree. It's just a root. Might even want to call it a seed. I don't know. But a tree is either a single node, or it consists of a root node with one or more children, where each child is itself the root of a tree. So A is the root node, B is the root of a tree, C is 2, D is technically the root of a tree because it is a single node. And then the exact same thing applies to all these nodes down below. And I just got an idea for a quiz question, which leads me to want to emphasize it's good to remember that a tree is really just a type of graph, and it may help, or it will definitely help, to be aware of what is and what isn't a tree. So since this figure here is a graph, if I drew an edge from D to G, that would still be a graph. The definition allows me to draw this edge, but this would no longer be a tree. Intuitively, you could see that this just sort of breaks the structure of like parents and children. But more precisely, going back to our non-recursive definition, a directed graph with no cycles. We can see that this is not a directed graph with no cycles. You could trace a path from A to itself. So this breaks the tree. We're going to be talking about trees and only trees for the next little while, but later in the course there will be more graphs, so you should know now or be able to tell between graphs that are trees and graphs that aren't. Going ever closer to our data structure, a binary tree, bi for 2, is a tree such that each node has at most 2 children. This lets us divide the children into the left child and the right child. And keep in mind that it's at most 2 children, not exactly 2. So If it had to always be exactly 2, the tree would go on forever because every single node would have children, and that node would have children, and that node would have children, and that node would have children. So but that means that some nodes have to be able to be leaves. Likewise, it's totally allowed for nodes to just have one child in a binary tree. In fact, the catastrophe, the fatal flaw of binary search trees that I've been alluding to may or may not happen when a tree or a binary tree has a whole bunch of nodes with just one child. And kind of going back to that idea of being able to tell apart things that are trees and trees that are things that tell the difference between trees and graphs that aren't trees. It's similarly helpful to be able to tell the difference between things that are binary search trees or binary trees and not binary trees. So if I add a node here, think to yourself for a few seconds. I won't make anyone put their hand up. Is this still a binary tree? I'm just waiting like 5 seconds or so. Right. Now, if I put a node here, is that a binary tree? And finally, where should I put this? What if I did that? So, answer key. This is still a binary tree. This change is entirely non-controversial. It looks like this could have been in the slide if whoever's presenting, perhaps me, made a last-minute decision to add another node. This was sort of a trick question. I could see this getting the reaction that, like, oh no, this is breaking the hierarchy. You can't just go up onto another level. But this is fine. It's kind of a crappy drawing. This node really should be drawn below the node that it's a child of, but like, it's still a tree. If you were representing this tree in a program, then it would be indistinguishable from something that is just fine, unambiguously a tree. Here, I gave node I not 1, not 2, but 3 children. So, since a binary tree is defined as having, or with each node having at most 2 children, that is not a binary tree, but it's still a tree because it's still a directed graph with no cycles. So to finish us off, I added a cycle. Now this is just a regular old graph. Nothing special about it. Binary trees have a similar recursive definition to regular old trees. A binary tree is either a single node or it's a node with at most 2 children where each child is the root of a binary tree. So A is the root because its 2 children are binary trees. B is the root because its 2 children are binary trees. E is a root of its own binary tree because its child is a binary tree. And finally, H is a binary tree because it's a single node. Cool. To actually represent a binary tree in code, we use similar ideas to linked lists. We have an internal node class where each node contains pointers, which could be null if the thing that it's pointing to doesn't exist, to its left and right children, as well as some data. And then the binary tree itself contains a pointer to its root node. And also the data could be a key or a key value pair for an entry in a table. So you can implement a table with a binary tree similar to, or not that similar, just repeating the idea of interface being totally different from implementation. You could have two tables with identical methods and specifications for those methods, but have it work completely differently internally because one uses a binary tree and one uses a hash table. Last thing I wanted to note before we move on is that the class shown here is nice and simple. It's pretty intuitive. But this structure kind of breaks down for more general trees that could have any number of children. I guess you could get around that by having an array of nodes for the children. But it breaks down a whole bunch when representing general graphs. Turns out having a node with pointers to other nodes to represent edges isn't really a good way to represent graphs in general. So this structure works perfectly for binary trees. But when we talk about graphs later in the course, we're going to get a bit more sophisticated. We're getting closer and closer to an actual data structure. These nodes are numbered. This binary tree contains a set of numbers just like an array could hold, in this case, the numbers from 1 to 9. And the way that this tree is arranged, the way this tree is arranged, by that I mean the specific positions these numbers are in, satisfies a thing called the binary search tree property, which means that for any node in the tree, all of the values in its descendants, or in the left subtree, is less than that node, and all of the values in its right subtree are greater than that node. So 1, 2, 3, and 4 are all less than 5. 6, 7, 8, and 9 are all greater than 5. So the property holds at the root. Likewise, for 6, 8, 7, and 9 are greater than 6. Cool. And with 8, its left child, 7, is less, and its right child, 9, is greater. So the property holds recursively for the entire right side of the tree. And it holds on the left too, but checking that would be redundant. Up to now, we've just been talking about binary trees. That's a tree where each node has at most 2 children. And now getting more specific, a binary tree that has the binary search tree property is called a binary search tree. Yet another recursive definition, a binary search tree is either a single node or it's a binary tree with the binary tree property. Yeah, and where all subtrees rooted at the left root and the right root are themselves binary search trees. Okay, I'm going to give you a bit more time to think about this one. I think I'll set aside 2 minutes or something. You'll get the most value out of this if you haven't looked ahead of the slides, but no worries if you have. Try to think of an algorithm for finding the minimum and the maximum entry of a binary search tree. Wahoo! Hopefully you thought of something. The sort of canonical algorithm for this operation is to just keep moving to the left until you reach a node that does not have a left child. Very simple idea. Look for the one that's leftmost. Look for the beginning of the list. But it might have been a bit more complicated to actually get that into pseudocode. And also, I hope that was a good warm-up for something else you might want to think about ahead of when I just tell you how to do this. And that's traversing the tree. How might you move through the tree in order to print out all the values of it in order? You don't have to worry about that yet, but you might have to worry about it in a couple minutes. You can do this iteratively or recursively. In an iterative version, you might have a while loop saying while current dot left child is not null. You can also do it recursively, where you want to find the minimum value of a tree, and you do that by getting the minimum value of the left subtree. So the minimum value of this whole thing is the same as the minimum value of the subtree rooted at 12, which is the same as the minimum value of the subtree rooted at 6, which is the same as the subtree rooted at 2, which is 2 because 2 doesn't have a left child. And then the satisfying end to a recursive function, it just return, return, return. To say that the minimum value of the tree rooted at 18, the actual root, is 2. The exact same ideas apply for the maximum of a binary tree. If you want to find the maximum, you can keep traversing the tree to the right until you find a node that doesn't have a right child, in this case 40. And you can also do it recursively by finding the maximum value of the tree rooted at 18, by finding the maximum value of the tree rooted at 27, by finding the, you know what I'm saying. The exercise for the reader is what you just did, and I am at the end of the slides for this week, so yay for that. We've still got 20 minutes, so I'm going to dig up what I hope is next week's slides. Not exactly fully prepared, but should be good enough for me to lecture with. If I go or if I see something and go hold up, I need to majorly revise this before I present it, I'll just stop the class. But for now, it's good that we're getting ahead, because even though it definitely can be stressful to get content this quickly, it's way, way better than being behind and then having to cram anyway. I was hiding my laptop screen while I was pulling up the file because I didn't want to accidentally show off something sensitive, like anything that happened to be on my desktop while I was lecturing. But while I was on my desktop, I got distracted by something that isn't too sensitive and I want to show off. The assignment 1 results will be published very soon. I apologize for the delay. I had some procedural stuff to do with an academic dishonesty case. So I want to show off the overall results. This is kind of exactly what you want to see in these sorts of results. An average of about 80. Honestly, I would want to see 75, but I guess no one got that. Average of about, oh yeah, I guess I was looking at the node. The mean is 71, median 77, close enough to 75. With any assignment ever, there will be students who will do badly no matter how much you help them, and students who will do amazingly no matter how much you challenge them. And you want the majority of the students to still do well, 80%-ish. So good job, y'all. Now let's look at next week's stuff. Just more binary search trees. Recall the binary search tree property. All of the data, or all of the numbers stored in the left subtree are less than the root, and all of the numbers in the right subtree are, greater than the root. Now, after all that preamble about graphs and what they are, we're going to see a very good reason why you would want to use a binary search tree in a real program. Because remember, the data structures we've seen that have fast searching ability, so arrays and hash tables, are quite rigid in in how much memory they use. Linked lists, on the other hand, are much more flexible and dynamic in terms of how much memory they use. You just allocate memory for each new item that you add. But you're forced to use linear search, which is O of n, linear time. Binary search trees let you keep the flexible memory allocation of a linked list, but they let you use binary search. Wow. We're going to look for the value 32 in this tree. 32 is greater than our root value, 18. So because the tree has the binary search tree property, we know that wherever 32 is in the tree, it has to be in the right subtree of 18. So we check out 27. And just like that, the logic for the minimum and maximum example we saw earlier, the procedure can be done iteratively or recursively. Iteratively will be a bit more of a challenge, but the recursive algorithm you could probably imagine right now. We see that the value to search for is greater than the root, so we search the right subtree. Now we just keep doing that. On the right subtree, we see that 32 is bigger than 27, the root, so we search the right subtree. Now 32 is less than 36, so we finally diverge from that max algorithm we thought of earlier. We look for 32 by searching the left subtree. And then, would you look at that? 32 is equal to the value of the root. So we found it. That's what a successful search looks like, but you're not always looking for things that you'll be actually able to find. So your algorithm has to handle a case where the thing you're searching for doesn't exist. So say you're looking for the value 14. You start at the root that has value 18. 14 is less than 18, so we move left. Recurse, search the left subtree for 14. 14 is greater than 12, so we move right. Search the right subtree. 14 is less than 15, so we want to move left. Search the left subtree. But that's impossible because the node with 15 doesn't have a left child, and thus there's no left subtree to speak of. If your search algorithm doesn't account for failed searches, you'd get a null reference exception right about now. But you're better than that. Your code would have some sort of null check. We see that node 15 has no left child and conclude that the value 14 is not in the tree. Write an iterative implementation of the search algorithm. I think that was supposed to say iterative. Minor spelling mistake. Like I mentioned, the recursive algorithm for this is a lot simpler, a lot easier to talk about. but an iterative implementation is much nicer for reasons that don't show up in asymptotic notation, but you hopefully learned about earlier. There's just some overhead in calling functions, or calling methods, I mean, for Java. And thus, even if they both run in O of n log n time, the iterative version will just be nicer on the computer because doing another iteration of a while loop takes less resources than calling a method. Now for insert. When we add a new entry to the binary search tree, we have to take care to preserve the binary search tree property because, like, if we don't, then it's not a binary search tree anymore, and all the logic that we used in earlier explanations and algorithms wouldn't apply. So if we want to add the value 30, we have to put a node with 30 in it somewhere in the tree, such that for each node, all of the values in its left subtree are still less than that node's value, and all the values in that node's right subtree are still greater than that node's value. Just at a glance, it's going to end up somewhere around here. Of course, computers don't work at a glance. You gotta be precise and iterative about everything so that your algorithm that works for trees that are 1, 2, 3, 4, 5 nodes high also works for trees that are 1,000,000 nodes high. So the insert operation starts with a search. You basically search for the value that you're adding, in this case 30. If it doesn't exist, so if the search fails, then you do the insert. If it already exists, then the thing that you do next is implementation dependent. Depends on whether your program, depends on whether it makes sense in your program for a tree to have duplicate values. Hopefully it doesn't, because that would kind of mess with what we've been talking about so far. So search. 30 is greater than 18, so we move right. 30 is greater than 27, so we move right. 30 is less than 36, so we move left. 30 is less than 32, so we move left. But there is no left child of 32, no left subtree of 32. Those two ideas are the exact same as long as the binary search tree property holds. So we found a blank space where this node should be, and that's where we add it. With our pseudocode shown earlier, this would just be a matter of changing 32's left pointer from null to a new node containing 30. With more complicated graph implementations, it could get weirder, but we don't have to worry about that for now. Ooh. Does this have the answer? Okay, cool. I wonder how I should handle this. Yeah, like we're already quite a bit ahead of schedule, so I want to go through this rather slowly. And we also have 4 minutes left in this class. So like, do this if you want, but class dismissed, and I won't be offended if you leave immediately. So good luck on the quiz, and I'll see you all again on Friday.